Okay, great. We're back. So yeah, like I was telling everybody before I started recording, for today's video or for today's class, I don't have a explicit plan as far as like specific material that I want to cover. Instead, this is a day to generally talk about the first part of this class and the things that we did there, the sort of skills that I want you to review. The first few weeks of class, at least in my opinion, felt a little bit like a sprint in which we were really trying to master a large number of integration techniques. And so we were sort of in a position where we were calculating or we were learning a new integration technique basically every day. As a result, it felt really frantic. At least I don't know if you all felt that way. I felt kind of frantic while we were teaching it. There was a lot of material that we had to absorb relatively quickly. And then we saw these integration problems where our goal was to try to integrate using any means necessary, which means that we had to look at the integral problem and figure out what made sense as far as like which integration technique might work, which integration technique might not work. And so what I have here today is I really just have a copy of the first test, which I was going to go through with you all and just try to solve some problems, sort of eyeball the ones that I thought looked particularly challenging. And along the way, I also want to look at these integrals and think through how I might go about solving those if I were faced with them on a quiz or on a test. So I'm going to start doing that. I know we've been sort of, this has been more lecture based and you all have been a quieter audience than when we were in class. So I'm just going to talk through these, but please interject if you have questions, comments, or concerns going forward. Maybe just before we even get to any specific problems, a quick list of the kinds of integration techniques that we wanted to have or that we had back in the day. Let's see if we can even remember all of these. So integration techniques that we had included U substitution, right? And that was what happened when we took a part of our integral and we let it equal u. We took its derivative and let that equal du, and we were able to essentially do a change of variable, replacing all of our x's or an appropriate expression involving x's with u's. So we had u substitution. We had integration by parts, right? And that had the formula, what was that? That was the integral of u times v prime is equal to u times v minus the integral of v times u prime, or alternatively, this is sometimes written as u dv equals uv minus the integral of v du, right? But it meant taking our original integral, which was kind of in this first form here, and sort of recognizing it was in this form, so identifying a piece that could be our u, a piece that could be our v prime, and then replacing it with this expression here. And the hope was that in doing so, right, our answer would not be completely done. We'd still have this integral, but the hope is that this integral would be easier to compute than the first integral. So we convert a challenging integral into an expression minus a simpler or an easier integral. And that was sort of our plan there. We had a specific kind, well, maybe next I'll say sort of partial fractions, I think is the other really big one. So partial fractions was an integration technique in which you had an integral of some big like expression involving a rational expression, right? So there was some stuff in the numerator, there was some stuff in the denominator, and the idea was that this rational expression had a denominator that could be factored, right? And here I factored this into a bunch of squiggles times a bunch of dots, and then we could express this as an appropriate integral of something over the squiggles plus something else over the dots. So again, it was an idea of, or it was this idea of taking a complicated looking expression, a complicated looking integral, and translating it into other integrals that were easier to compute, that were easier to integrate. And after that, we had a couple of, I'm not sure, I was going to say one-offs, but I don't think that's the right phrase. We had a couple of more specific techniques, I guess, less global than these three, but still specific. And that included, so we had something called trig sub, right? So trig substitution, that was often when we let x equal a trig function involving theta, right? So a trig function involving theta. And that's different than u substitution. I should say they're both similar in that they involve a change of variables, but u substitution typically involves saying let u equal some expression involving x, right? So an x expression, like u equals x squared or u equals sine of x or something. But in this case, we were letting our x equal, or in u substitution, we were letting our u equal an expression involving x. In trig substitution, we were letting our x equal an expression involving theta. And typically this was a trig identity, or a trig quantity involving theta. And usually the sort of hint for a trig sub was that it had one of these forms. It was either something like 1 over the square root of a squared minus x squared, 1 over the square root of x squared minus a squared, or 1 over x squared plus a squared, right? So it was like one of these three quantities that we were kind of on the hunt for, that we were keeping an eye out for. Typically involving an x squared in the denominator, plus or minus some constant was kind of the idea. So trig sub, that was sort of a special trick. We also had what we called these trig integrals. Right, and trig integrals usually involved using trig identities to simplify another integral. So trig identities like sine squared plus cosine squared equals 1, and other similar identities. So those were, again, maybe highly specialized, but we'll sort of keep an eye out for expressions only involving trig to see if we can use trig identities to simplify them. So those were our big list of things. We had sort of the three big ones: u substitution, integration by parts, partial fractions. We had our more specialized techniques like trig sub and trig integrals. The final few things that we talked about were not directly, integration techniques, but rather sort of more global ideas surrounding integration. So those were the idea of improper integrals, right? And those typically involved functions with either horizontal or vertical asymptotes. If you can read anything that I'm writing, that's supposed to say horizontal or vertical asymptotes. So we had improper integrals, which meant that we had to be careful in how we set up an integral involving a horizontal or vertical asymptote. And finally, we had this idea of numerical integration, right? This idea that some integrals are just too challenging to compute even with these trig tricks. I'm sorry, these integration tricks. And so as a result, we would try to get a numerical answer that was reasonably accurate. And there were different strategies or different, different strategies for doing so with different levels of effectiveness. Okay, so all that being said, those were sort of our big ideas early in the semester. More or less every single one of those corresponded to a given skill in the first 4 weeks of class. And that being said, let's jump into some of these. We won't have time to go through the entire test sort of piece by piece. So instead, I'm going to pick and choose some problems that I think are worth sort of pausing to talk about. So for these first few problems, I think both of these are substitution problems So I want to focus on how I recognize these are substitution problems and how I might make at least, or how I might start making my substitution. And I'll let you all pause the video if you're watching this later and fill in the details. So for each of these, if I think it's a substitution problem, and I'll often start by checking to see if it's a substitution problem, I will try to identify a good choice of U. And a good choice of U has sort of two main features. So we want to choose U so that U prime is in the numerator, by which I just mean, probably even saying in the numerator is kind of a misnomer. What I really mean is it's being multiplied by the rest of the expression, i.e. multiplied in. And I want to choose U so that U is in some parentheses, either explicit or implicit, parentheses, meaning that it's getting plugged into another function. So U is supposed to be some inside function here. And so if we think through this, maybe I should say both of these are sort of contingent on having both U and U prime are present in the integral. So what does that mean? Well, if we look at this first one, we see that we have just a few core components, right? We have this E, we have this root x, and we have this root x. And so at the moment, it's not immediately clear what our U might be. But if we think about it a little bit, I'm going to just take this first one to look at, right? I'm going to rewrite this as e to the root x times 1 over root x dx. And I'm going to sort of think about what I know about integrals, and I'm going to remember that the derivative of the square root of x, right? Well, the square root of x is just x to the 1/2, and so that becomes 1/2 x to the negative 1/2, which is 1 over 2 square root of x. So in fact, what I can see is that I have this square root up here, right? And that's sort of in parentheses, by which I just mean that that entire root x is up in the exponent. So if I had wanted to, I could have written that as e raised to the, and then parentheses, root x, times an expression that looks an awful lot like the derivative of root x. And here's why I said that saying that u prime is in the numerator is probably a misnomer, right? When I pulled the root x out, I see that it was really being multiplied by 1 over root x, and so the du is really being multiplied in. And it's not 100% being multiplied in. There's this constant term, right? There's this constant 2 down here that's currently missing over here. So there's a missing 2. And so we have to be sort of cognizant of that. So I guess maybe bullet point number 3, bullet point number something, adding to our list up above, right? One other thing that we can say is that constants multiplied in, like that 2, right, in the denominator, that's just multiplied in. Constants that are multiplied in are fudgeable. Very technical word, fudgeable, basically meaning that, you know, at the moment, I'm missing this 2, but I can easily add in this 2, and I'll do that here. Let me, I'll erase these parentheses, and I'll add in a 2 into the denominator by adding in another 2 into the numerator. And because everything here is being multiplied together, I can just pull that 2 that's being multiplied in, I can pull that outside of the integral, right? So because multiple constants that are multiplied are things that we can remove sort of in and out of the integral and sort of position where we want them to, that means that the constant multiple here can be fudged in by pulling out an appropriate constant. In other words, I multiplied the entire thing by 2 over 2. I pulled the 1, 2 outside, but that 2 in the denominator was left in. So at this point, I could say, let's let u equal root x. Let's let du equal 1 over 2 root x dx. And now we see that what we have written up here is exactly a du, while what we have inside the parentheses in our exponent is exactly a u. And so this entire thing can be rewritten as the integral, we have that 2 out front now, and this became e to the u du, which just becomes 2 times e to the u plus c, which is 2 times e to the root x plus c. And that would be our final answer there. So not only was this sort of like a nice review of u substitution, I hope that also helped sort of with the thought process of how do I know that substitution is appropriate, and how do I know what a good choice of u is, and how do I deal with those pesky constants. I'm going to take a long drink of water and see if there are any questions about that. Okay, if there are no questions, let's jump on to a different problem. Let's see what else we've got. So if that was substitution, scrolling down, I don't think either of these questions are substitution. And I think both of these, in fact, would benefit from integration by parts. So let's at least talk through what our thought process there is. And I guess it doesn't matter. Let's keep focusing on the first problem. So let's focus on this problem here. So for a problem like this, I might, again, think of it as potentially substitution, right? That's usually my first go-to. And so if I'm looking at this, I'm trying to hunt and see if there is a good choice of u in some parentheses with a du that's being multiplied out front. And I don't see that here because the thing that's being multiplied out front is most likely this x. And so this x would be, I guess that x along with the dx would be likely choices for u if u sub was appropriate. Now the problem is, in this case, in order for that to be, I'm sorry, these are likely choices for, I said u, I really wanted to say u prime or du. These are likely choices for u prime if u sub is appropriate. Now, as we look at this though, we notice that I don't really see a good choice of u to go with that du. In other words, if this was u prime, that would mean that u should be something like x squared. And we don't have an x squared here, right? Or it should be something like x squared over 2. But it should involve an x squared, a quadratic piece. And in the parentheses, all we have here is this 4x, right? Which is not an x squared. So in fact, what we can see here is that there is not a good choice of u and a good choice of an associated du. And so what do we do in that case? Well, we still have two pieces being multiplied together. In fact, we have a polynomial piece, right? This piece is a polynomial piece multiplied by an exponential piece. And if we have a polynomial piece times an exponential, or a polynomial piece times trig, which is the case in the second problem, if we're in that situation and u substitution is not appropriate, usually the go-to move is to use integration by parts and to let u equal the polynomial piece, right? Because if we let u equal x in this case, then when I go to take the derivative, or when I go to apply integration by parts, as a reminder, integration by parts looked like this. All right, so if I were to let u be my x, then this piece would be an x, that would be an x, and in this final step, we'd end up with something times x prime, which is just 1. So that would get simpler as I go through the integral. And we would end up with an integral that's just a little bit simpler. It wouldn't have that x in it. And again, because of potential time issues, I think we can leave the details, if you're interested, as something to think through maybe later today over a nice cup of coffee or something, right? But this sort of sets up the idea that integration by parts is a good choice here, letting u equal x, and then letting v prime equal whatever's left. So that would be the exponential e to the 4x dx. Okay, so that gives us a sense of integration by parts versus u substitution and when we might use one over the other. As we keep going, we're going to end up with these two next problems, right? These two problems on the next page. I will point out that I think this first problem is a great candidate for partial fractions, right? And the idea there is going to be that we have a polynomial, not a polynomial, a rational function. So it's something divided by a polynomial. In this case, it's just a constant divided by a polynomial, so that's great. And this polynomial in the denominator, well, let's think through it. We can actually factor this, right? That can become, and I can rewrite this integral as something divided by, and that's going to be an x plus 6 times x plus 2. And that's all over 4 right there. So if I try to calculate this integral according to partial fractions, this should be a something over x plus 6 plus a something else over x plus 2. And now the question becomes, what is a and what is b? Right, so in the game of partial fractions, we would have to take this expression, we would have to multiply, and maybe I didn't quite give myself enough room here, but we would want to multiply this first term by x plus 2 over x plus 2. And the second term we'd want to multiply by x plus 6 over x plus 6. And so what we get then is we end up with an expression, maybe I should have paused. Before I go further, I would say my goal, before I start writing in this dark blue pen, my goal is to figure out what values of a and b let this first pink integral, right, this one right here, equal this second pink integral, so without the sort of dark blue markings on it. In other words, what are a and b that let these two things be equal? Once I know that, I can replace the first integral with the second integral. And so as a result, I can then solve what is theoretically a simpler integral. So our goal is to figure out what a and b each are. And to do that, I sort of rewrite this expression under a common denominator. And that would give me, I think I have an extra squared there that I don't need. That should just be an x plus 2. What I end up with, though, is I end up with an x plus 6 times x plus 2 over a times x plus 2 plus b times x plus 6. And this is great because these two have the same denominator. And if they're equal to each other, they should have the same numerator. In other words, we can solve for a and b in the sense that a and b must satisfy 4 equals a times x plus 2. Okay, there we go. A times x plus 2 plus b times x plus 6. And now we can explicitly solve this by grouping the x terms together. So that's a plus b. And then grouping the non-x terms together to get 2a plus 6b, right? And so each of these are treated separately. For this term, right, the x times a plus b, we have to recognize that there is secretly a 0x over here. So 4 could be interpreted as 0x plus 4. And so 0 equals a plus b, while separately, we know that the 4, so when we get to plus 4, 4 should equal 2a plus 6b. Right? And so then the goal becomes trying to find values of a and b that simultaneously satisfy a plus b equals 0 and 2a plus 6b equals 4. And so I think we can end up with b equals 1 and a equals -1 here. Right? And to make that leap, note that in this first equation, this means that a is equal to -b. So a and b are, just plus minus the same number. And we can think through what values can give us 2a plus 6b equal to 4. So when it comes to partial fractions, a lot of the challenge is in this setup, right? We haven't actually computed any integral yet. And so let me sort of jump back here. Our goal was to figure out an a and a b that could replace this top integral with this next integral. And so now I think we've done that. Through all this hard work, we have figured out that that first integral is actually equal to -1 over x plus 6 plus +1 over x plus 2. And the idea is hopefully that these integrals are easier to compute, easier to integrate than our original integrals. And in this case, that's absolutely the case. Each of these would end up being a natural log expression, right? We could do a substitution. U equals x plus 6 in the first one, u equals x plus 2 in the second one. And so we end up with -ln of x plus 6 plus +ln of x plus 2. So a great, fun partial fractions problem to kick things off. Well, to kick off problem 3, I guess. So let's see, what else we have? If we jump down to this problem, maybe I should say, so we had to keep going with that first problem. We would have to eventually evaluate these endpoints as well. I sort of glossed over that. So we would want to find not just the antiderivative, but we'd want to plug in those endpoints to calculate that. For this one, it's a similar problem in that we would have to find an antiderivative for this expression and then use the fundamental theorem of calculus, plug in those points there. This is a great example of a trig substitution problem, right? And it has exactly what we were looking for. It has that square root sign in the denominator. It has a something squared minus x squared, right? Specifically, this has 5 squared minus x squared. And so we can remember, right? And this was something that we had to memorize back in the day, and I would encourage us to review this. But we can remember that something squared minus x squared in this denominator often benefited from a substitution of x equals that number, in this case 5, because it's 5 squared. So x equals 5 sine of theta, where the sine was coming from the fact that this was something squared minus x squared. So x equals 5 sine theta in this case. Just like in the case of u substitution, we would want to calculate an associated differential piece, dx. So in this case, dx equals 5 cosine of theta d theta. And now we get to do a substitution, but the substitution is slightly more straightforward than in the U substitution case. I'm just going to plug in wherever I saw an x or a dx, I'm going to plug in these values over here. And then the real trickiness will come in how we manipulate that denominator. So the denominator, that becomes a 5 squared minus x squared. And so x squared, that became 5 sine theta squared. Didn't quite give myself enough room. And then on the outside, we're multiplying by cosine of theta d theta. Right, so I made the substitution that the problem kind of demanded, right? Just based on what we had learned about trig sub. I've plugged in, and now there's a question of how far can I simplify this? And it turns out the denominator, because I have these 5 squareds, I can actually factor those out. I guess there's a few different ways I can think about this. One is that I can factor out the 5 squared. So I still have this big square root sign, but I have a 5 squared times, in parentheses, 1 minus sine squared. Up here I have a cosine theta d theta. But, right, 1 minus sine squared is a trig identity. We have our old friend cosine squared plus sine squared equals 1. And so 1 minus sine squared is nothing more than cosine squared. So that actually becomes, after simplification, 1 over 5 squared times cosine squared of theta. We still have this cosine of theta d theta out here. Oof. There we go. Okay, and then this becomes the denominator. I can take the square root of each of those, so that becomes a 5. That becomes a cosine of theta. And then over here, I've still got my cosine of theta d theta. So it actually simplifies considerably. The cosine theta and the cosine theta will cancel with each other. Ooh, yes, okay, there's a great question here. Hang on one second, I'm gonna finish this thought. Okay, so after the cancellation, what I would be left with in this case is just 1/5 d theta. Now, there is a question Carson is asking about cosine theta d theta instead of 5 cosine theta d theta, and I think you're right. Let's go back and double check. So it looks like I've lost a 5 here. And the 5 came from this piece here. Yeah, so my dx had to be replaced with a 5 cosine theta d theta, and it looks like I lost that. So there should have been a 5 here. Thank you, Carson. Yeah. And Alex, it looks like, were you going to say something similar?
I was gonna wait till the end, but since you asked, you
Sure.
picked 5 sine theta because of the structure of what's under the square root, right?
Yes, 100%. So the sort of structures that we're looking for in these kind of problems are either a squared minus x squared, and that becomes the choice that we make is a sine theta. We have an x squared minus a squared. That was really the odd one. I think we only saw one example, maybe 2 examples like that, where it was a secant theta. And then x squared plus a squared, the choice was a tangent theta. In general, I think the most important ones to know are the first and the third. Those come up reasonably often. But yes, so in this problem, it was that first one that we really focused on. So because of that structure, that's why we chose the 5 sine theta. Okay, and then going back to Carson's point here, there should have been a 5 in all of these, which is great, actually. We can simplify this because now that 5 and that 5 cancel. And so this is really now just the integral of d theta, right? Because our variable is theta at the moment, that becomes theta plus a constant. And the final step in these kind of problems is to try to rewrite it in terms of x. And so we have to go back to this piece, right? X equals 5 sine theta. And we have to say that if x equals 5 sine theta, that means that x over 5 is sine theta. And so theta is going to be arcsine or inverse sine of x over 5. So we have to resolve for theta in this case. And so our answer is actually not just going to be theta plus c, it's going to be inverse sine or arcsine of x over 5. And to completely tie a bow around this problem, we'd actually want to go all the way back and remember that we have to plug in the number 5 and the number 0, right? So this is a definite integral, and we'd have to compute maybe as a final answer. The hell, we're only one step away. Let's give a final answer. Final answer would become arcsine of 5 over 5, so that's arcsine of 1, minus arcsine of 0 over 5. Right, and that would be a perfectly acceptable final answer. Arcsine of 1 minus arcsine of 0. So for these trig subproblems, I think a lot of the challenge is actually in this first step. You can feel kind of lost if you don't remember what the nice substitution to make at the beginning is, right? Because there's a lot of, or it's not intuitive necessarily, especially if you haven't looked at it recently. But once we remember that, or once we have the opportunity to review that, and if we feel good about that choice, the rest of it follows reasonably naturally, right? You make the substitution, you use the appropriate trig identity, you simplify everything down, and that will often give you a appropriate integration to do. Okay, let me see. I want to be sort of conscious of the time. I'll tell you what, give me 2 seconds. I'm going to scroll through the rest of the sheet and think through what problems I definitely want to talk about. If anybody has any problems that they definitely want to see from this first test, feel free to leave it in the chat window. Otherwise, in about 30 seconds here, I'll make an executive decision. Okay, I'm just thinking out loud here. I definitely want to talk through problem 10. I remember that being the most missed problem on the first test. And I at least want to talk through sort of like the key idea there. I think either of problems 6, 7, or 8 could be worthwhile. 8 is a little bit of an odd one, or it has the potential to be intimidating. So maybe focusing on, yeah, I'm gonna say this. I'm gonna try to jump down very quickly to 6. Then I'm gonna jump down to at least 9, 8 and 9. And if I have time, we'll either do some of the numerical analysis questions or sort of circle back up here. This was a set of, these were 4 slightly challenging integrals that we explicitly talked about in class. They required, sort of extra tricks that didn't nicely fall into any of the other categories per se, or rather maybe they did, but they required some outside the box thinking. Each of those was one that we explicitly computed in class. And so for that question, it was really a question of, do you remember these important integrals that we discussed in class and how we went about solving them? And as long as you got 2 of the 4, I was happy. So if we have time, we'll circle back around to there. I'll briefly mention this. I think we can polish this off in about a minute and a half, because this is an example of that trig integration, recognizing that there's a clever trick we can do with trig identities. Specifically, this problem, we have this cosine to the 5th, and that means that we want to break this up into cosine to the 4th times cosine. Right? If we didn't explicitly see that, I would point out that this is nothing more than cosine times cosine, 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 right? Cosine of the 5th is just 5 copies of cosine. And one of our tricks, right, one of our trig identities that we love and that we use surprisingly often is this fact that cosine of x squared plus sine of x squared equals 1. So if I have two copies of cosine, like cosine times cosine of the same thing, I can replace that. So cosine squared is equal to 1 minus sine squared. And that can be really helpful in these trig integral, trig identity style problems, because what we have here is an odd number of cosines, which means as I pair them off, I can get this cosine squared becomes 1 minus sine squared. This cosine squared becomes another 1 minus sine squared. And then I have this lone cosine, which, I mean, it's a little sad, it's a little lonely, but for the purposes of this integral, it's actually really useful. Because when I go to rewrite this integral, I'm going to rewrite this as 1 minus sine squared of x squared times this lone cosine. And if you think back to what we discussed in terms of substitution, you'll recognize this is a really good U substitution problem. It has an expression in parentheses, namely sine of x, whose derivative is just multiplied off to the side. So U prime is cosine. And the fact that there was a lone cosine, a lonely little cosine, actually means that it by itself floating off to the side in the multiplication makes a great du. So we could actually rewrite this using U substitution as 1 minus U squared squared times du. Right? And though that looks a little challenging, we could explicitly compute, right, 1 minus something quantity squared. That could become 1 minus 2u plus u, I'm sorry, minus 2u squared plus u to the fourth du, right? So we could just FOIL out this expression here. So once we recognize that trick, we can get this one reasonably quickly, or at least develop a framework for getting it. One of the key observations is that we had this cosine expression and that number up there was odd, right? That's what allowed us to peel off this lonely cosine. That would make an excellent du. And similarly, anytime we have an expression of the form sine to the something times cosine to the something, if one of those two numbers is odd, then we are in a good place to use this trig trick. Right? So I think an example that we might have talked about in class, or if we didn't, we easily could have, and I'm just sort of making it up off the top of my head, but if we had the integral of, let's say, cosine to the 10th times sine to the 7th, that'd be great. We have an odd number for the sine, so we could break this up, peel off a lonely sine, and make that lonely sine be our du, meaning that our cosine expressions would have to be our u. So that could be our trick there. Okay, jumping down, let's talk through problem 10, because I think, if I remember correctly, problem 10 was the most missed problem on the test, this first test. And the trouble is you're inclined to try to compute this just sort of straight up by applying the fundamental theorem of calculus. You know, whoops, let me try that again. You know that an antiderivative of 1 over x squared, well, I can rewrite that as x to the negative 2. And x to the negative 2 is negative x to the negative 1, is the antiderivative. Right? So a lot of people recognize that, and they were quick to say, okay, this is negative 1 over x, right? That's what negative x to the negative 1 is. That's negative 5, that's 10. And so if I plug that in, that's going to give me negative 1/10 minus negative 1/5. Easy peasy, done. But unfortunately, incorrect. So what was the issue here? Well, the issue is a super, super subtle one. It has to do with this function and the domain that we're currently looking at. So the domain that this is defined on. And a little bit of intuition is necessary here. So you don't have to be able to graph this function, though I think you're all sort of more than capable. You know that 1 over x, or 1 over x squared, or 1 over x cubed kind of looks like this. It has this interesting asymptotic nature to it, right? So 1 over x, or 1 over x squared, or 1 over x to the n, where n is a positive integer, kind of looks like this. If I'm making it x squared, right, what that will mean is that it looks the same when it's negative as well, right? Because when I plug in negative numbers, I square them. It's the same as if I had plugged in the positive number. I get the same output. So my function 1 over x squared roughly looks like this. And if I'm integrating from -5 up to 10, there is going to be a major problem point here at x equals 0. We're going to have a vertical asymptote, which means that I cannot compute this integral straight up, right? As a reminder, the fundamental theorem of calculus said that I could compute the integral from a to b of f of x dx, and I would get an antiderivative at b minus an antiderivative at a. This only works if little f is continuous on the interval from a to b. So if our little f is continuous all the way from a to b, here's a function, 1 over x squared. It is not continuous from -5 all the way up to 10. There's a big problem point at x equals 0 that corresponds to a vertical asymptote. Now, you might not have remembered exactly in the moment that 1 over x squared looks like this, and that's okay. But we want to be able to look at this and think, x in the denominator, x squared in the denominator, that's going to be a problem if the denominator is 0 and the denominator equals 0 at x equals 0, right, at x equals 0. So we know that there is something kind of rotten happening here. And so we have to sort of pause and think carefully and go forward carefully as we evaluate this problem. And to the rescue, right, are our improper integrals. Improper integrals were developed exactly to handle these kind of problems, the problems that came with vertical or horizontal asymptotes. So what we're going to do is basically function surgery or integral surgery here, right? We're going to split up. So I'm just going to call this function f, right? So 1 over x squared is function f. So we had the integral from -5 to 10 of f. We need to split this up, sort of slice at 0. So this should be from -5 to 0 plus 0 to 10. And then I need to carefully evaluate each of these integrals using limits, right? That was the nature of our improper integrals, was we carefully, surgically avoid the issue by taking a limit. And this should be the limit as x goes, as b goes to 0 of f plus, and then we'd similarly have an integral not from 0 to 10, but from a to 10. And we would take a limit as a goes to 0. And if we're being really precise here, a should go to 0 from the right-hand side, and b should go to 0 from the left-hand side. So I'm evaluating these two integrals separately, not all the way from -5 to 0 and from 0 to 10, but from -5 to some nearby point, b, that's on the left-hand side of 0. And then here from a up to 10. And then for each of those separately, I'm letting my a or my b sort of inch closer and closer to 0. So that's how we carefully tiptoe around this issue. And if we did this, right? Notice for the first integral, let's focus on this second integral, I think just because it's a little more intuitive. We would get the limit as a goes to 0 of that integral. Our work from before holds true. The antiderivative of 1 over x squared is negative 1 x to the negative 1. And so that becomes negative 1/10 minus a negative 1 over a, limit as a goes to 0. And as a goes to 0, this thing blows up. So this entire limit diverges to infinity. Full stop. We can't compute the rest of it. This overall integral is now known to diverge. So I think this was, again, one of the trickiest problems because the tricky nature of it was kind of hidden in the problem itself. We had to think a little critically about the function we were looking at and the interval we were looking at before just immediately jumping into sort of computational plug and chug there. Any questions about that problem? All right, cool. Man, that's a fun one. I do enjoy that problem. Okay, let's double back. I said we would double back. Let's look at 8. Yeah, we said we would look at 8. And then if we have time, we'll go back and look at some of the problems from 5. Or if other people have suggestions on what they want to look at, I'll follow your lead. But problem 8. Problem 8 has the potential to be super intimidating because it's a little abstract, it's a little weird. We're given this function w in which we are trying to compute in which we're trying to compute a certain integral, right? So we're trying to compute this thing. This expression involves the number w, it involves the function w, but we don't actually know what this function w is. And so as a result, again, we can't just blindly plug and chug. We can't start using our integration techniques because I don't have a w to plug in. I need to think a little more abstractly about what this question is really asking or how we can even begin approaching this. Because our w is unknown and because our integral involves a w or a w double prime, we are going to have to end up with an answer that has some expression of w in it. Likely involving w's and also w primes. And we're given a lot of information up here. Turns out we're probably given too much information, or we're given more information than we actually need to do this. So what we have here is we're trying to integrate the expression 2x times w prime prime, second derivative of w, at 2x. Thinking about our integration techniques, at the moment I have the multiplication of two expressions. That suggests to me that I either use u substitution, in which my u is inside the parentheses and my du is outside the parentheses, or I use integration by parts, in which I let one of my multiplication pieces be a u and the other multiplication piece be a v prime. I think in this case, we can start by approaching it either way. And maybe
Can you do integration by parts?
Yeah, that's what I was going to say. I would like to do integration by parts here. Let's take a look and see what we can do. So we want to integrate by parts. Again, the integration by parts formula. This is what I do, by the way. This is just like my little tip. Whenever I have to do integration by parts, I always write the integration by parts formula off to the margins. That really, not only does it mean I can stare at it while I'm talking to you, but the fact that I write it every single time really helps me remember it. So we have this kind of expression for integration by parts. Notice that in the process, again, our goal is to start with this expression. So we start here. And then the goal is that we end up here. And in particular, that this second piece is a slightly simpler integral. So we have to identify a good choice of u and a good choice of v prime. Because of the multiplication, I think one of these two pieces will be a u and the other one will be a v prime. And I'm pretty sure that I want this w to be my v prime. Now, the reason for that is that if you look up at the top integral, we start with a v prime. Let me grab a better contrasting color. We start with a v prime, and we end up with a v. So over the process of the integration by parts, v prime gets integrated. I'm not going to be able to write that up there. I apologize. V prime gets integrated as you go from across the formula. So what I have here is a w prime prime. And what I have up here is information about w and w prime. So part of me hopes that through the integration by parts process, my w prime prime gets integrated up to a w prime or a w. So whether I recognize that right away or just through some trial and error, I think integration by parts with this second piece equaling v prime should be appropriate. And for this first piece, we'll let the 2x be our u. So what I will often do in these kind of problems, once I think I've chosen my u and my v prime, I'll write those down somewhere. So we have u equals 2x. We have du equals 2 times 1 dx. We have dv is w prime prime of 2x dx. And then v, right? We have to figure out what this is. This will actually be, and let's think through this, w prime of 2x divided by 2. So it's the divided by 2 that might throw us a little bit. But notice, right, because we have not just an x in the parentheses, but a 2x, taking the antiderivative of this would require undoing the chain rule. In other words, secretly, in this one arrow that I've drawn, there's a subtle u substitution process that's occurring, right, in which this 2x is really like a u, and then I have to introduce this extra 2 in the denominator to get the du. To check this, we can note that the derivative of w prime of 2x over 2 equals, well, by the chain rule, we would get w prime prime of 2x times the derivative of 2x all over 2. And those 2's will cancel. So there's a potentially subtle piece to miss there. But when we take our v, we would end up needing that divided by 2 element. And so according to the integration by parts formula, the antiderivative of 2x times w prime prime of 2x equals u times v. So that's 2x times w prime of 2x divided by 2 minus the integral. And now we have our v, so that's w prime of 2x over 2 times our du, so times 2 dx. And of course, a lot of 2's here in the numerator and denominator can cancel. So we have that cancels with that. That cancels with that. And we can rewrite this. Oh my goodness. Holy moly, we're basically out of time. I'm going to finish this problem because I don't want to leave you hanging here. But I understand if you have to run away. It is 9:15. I know some of you have other classes. I think I can finish this in less than 5 minutes. I'm gonna power through. So this becomes x times w prime of 2x minus the integral of w prime of 2x dx. Now to integrate this second piece, right, this is again a substitution process. In fact, it's the same substitution process that we did up here, right? So the antiderivative of w prime of 2x will end up being w of 2x divided by 2. That will be the antiderivative there. And so what we get then is that our final antiderivative can be written as x times w prime of 2x minus w of 2x all over 2. And so that's our antiderivative. Now, the problem is not completely done. This is a great first foray, and this gets us most of the way there. But going back to the original problem, remember, this was a definite integral. And so we had to find an antiderivative and then plug in these two boundaries. So we had to plug in x equals 0, we had to plug in x equals 1. And we had all of this information to help us out. So we had, we had all of this stuff up here, right? Or I should say everything in this line has the potential to help us out. So let's write out what we have accomplished here, right? So what we have here, when I plug in 1 and I plug in 0, this will become 1 times w prime of 2, right? 2 times 1, minus w of 2 times 1 divided by 2. That's what happened when I plugged in 1, minus what I get when I plug in 0. And when I plug in 0, I'm going to get 0 times w prime of 0. I'll just go ahead and write that out. 0 times w prime of 0 minus w of 0 divided by 2. And what does that end up giving us? Well, when we plug in, we notice that w prime of 2 was 14. So that's going to be 14 minus w of 2 was 8. So 14 minus 8 over 2 minus, and then it's 0 minus, and then w of 0 was 5. So that's w of 0 over 2. So 5 over 2. And then we can simplify this. 14 minus 4 is 10, plus an additional 2.5. It looks like our answer will end up being 12.5 in the end. And yeah, that does it. So I think that's a nice challenging problem in that it involves, two integration strategies, right? We had to use integration by parts, but then in some of these steps, like in this step here and in this final step here, we had to recognize that there was a u substitution giving us an extra factor of 1/2. And on top of all of that, we had a very sort of abstract problem in which we had this unknown function w that we were trying to manipulate while leaving it unknown. So, fun, challenging problem. I hope that was helpful to all of you as a way to sort of refresh yourself on the stuff we did early in the semester. I know there was stuff on this test we couldn't cover. That's a-okay. Hopefully we'll have time in the future, either through office hours or review sessions, to discuss anything else that you had questions on. On Wednesday, my plan is basically to do the same thing, but with test 2. If you have explicit suggestions on things that you really want to see, please let me know. I'm very happy to tailor this towards your, sort of suggestions or your questions. Otherwise, have an absolutely wonderful rest of your Monday. And I will hopefully talk to you and see you soon. Take care, everybody.
Thanks.
Have a great day. Thanks, Alex. You too.